time. So we take the conformity theory to be in a compact space, and then the dual geometry is AdS5, AdS d plus 1, and here we draw a diagram where time runs up, goes up, this is the radial direction, and for some purposes it is useful to think of the CFT as living on the boundary, even though this is not completely accurate. And of course the idea is that anything that happens in the interior of AdS is encoded in the CFT. More precisely, in some sense, S-matrix elements in AdS are related to correlation functions in the CFT. So there's a mapping between fields, operators in the conformity theory, and fields in AdS. So this mapping is worked out. Any field that you give me in gravity, I know how to map it to the CFT. And correlators of this field O are related to, in some sense, S-matrix elements of this field in the bulk. Now, if the CFT is in the ground state, then the dual geometry is AdS5, AdS. So, metric. The basic idea is that so you can think of this space as a space where there's a confining gravitational potential. As you see, this relative factor grows as R goes to infinity. So the boundary of AdS is as R goes to infinity. But there's an attractive potential which is pulling everything towards the center of AdS. And the claim now is that the Hilbert space of the theory in the bulk is equivalent to the Hilbert space of the theory in the boundary. So all these questions about black holes we can try to address in the context of AdS50. Now, let me make some more precise statements. So it is useful to think about a very basic example of AdS50, which is the equivalence between the n equals 4 square wheels. It's a four-dimensional quantum field theory with Gauss group SUN, and that will be string theory on AdS5 times S5. And what I want to mention here is that when we have this correspondence, there are a few parameters that we need to tune in order for the bulk theory to be described by gravity, by classical gravity, semi-classical gravity, not string theory. And there are two of these parameters. One is n. We need to take n to be very large, because in AdS50 the radius of curvature of AdS is given by n to the 1/4 times the Planck length. So if we want the radius of curvature of AdS to be much bigger than the Planck length, we need to take n to infinity. And also the radius of AdS is related to the string scale by lambda to 1/4, where lambda is a Toth coupling. And it is easier to work with gravity rather than string theory, so we'll be working with the limit where lambda is much bigger than 1. So in this limit, the bulk height of the correspondence reduces to supergravity on AdS5 times S5, and for all purposes of my talk, this integral theory will not play any role, so from now on I will just forget about it, and I will talk about string theory on AdS5. But if you want to make it precise, you have to restore all this the eternal manifold, and you may have to take into account effects coming from string theory or gravity. Okay, so we said that the Hilbert space of the two theories are equivalent, and in gravity we can consider black holes in AdS. So a black hole in AdS has a metric which is very similar to this one. So here is some number times G over R to the D minus 2. Okay, so you have black holes of any mass. You can say the mass of black hole in AdS. And I want to remind you that in AdS there are two classes of black holes. There are black holes. So if the horizon radius is of the order or larger than the radius of AdS, this we call big black holes in AdS. And if the horizon of the black hole is much smaller than the radius of AdS, it's a small black hole. So small black holes in particular, small black holes in AdS will behave very similar to black holes in flat space, because the size of the horizon is much smaller than the cosmological scale. So we can approximate a black hole in flat space by considering a very small black hole in AdS. Sorry, what is my limit? No, I think it's okay, right? black hole by writing a similar formula as the one we had before. So if you want to talk about multi-planet horizons, then we need both the usual modes, the thing we had yesterday, these are the modes coming from the boundary, as well as these new guys that we're looking for, coming from the left. And if you put these two together, and you multiply them with the appropriate solutions to the Planck equation of the interior of the black hole, then you can reconstruct things which will reproduce correlators even inside the black hole. Or you can try to copy correlators across the horizon, and you could try to verify whether any one observer will detect deviations from GR. So let's make an operator like this, the conformity theory, and then calculate correlate functions and prove the truth of the horizon. Now this is here the why we use Forest modes. For example, if you're an informed observer, you can do, you start, if you're an excitation with modes, then you call time horizon, then you can do an experiment where you produce a pair of particles, one that moves to the right, the other moves to the left. So if you want to be able to describe an experiment, you definitely make both sets of modes. You cannot do it just with the modes from the exterior. If you remove this mode, then as we said earlier, what happens yesterday, there will be an attachment between the interior and the exterior, and the horizon will become singular. So for the smooth of the horizon, you need to have both sets of modes. Now, before we move on, let's try to identify formally what are the properties that this operator can satisfy in order for horizon to be smooth. So the properties that I will explain in the next slides are properties that you calculate using effective theory in the bulk, assuming that the horizon is smooth. So you assume that the horizon is smooth, you expand your field in the bulk in a mode, and then you try to identify what are the properties of the operators where one is smooth. So here are the properties. First of all, I don't want to include all the fields. So for every field that comes in the exterior, you have the mode in the exterior, or the mode that comes in the exterior of the you have the same modes for every field in the theory. So there is a mapping from the mode of the field that has to be 1-to-1. And moreover, the other of the field has to be something I want to go to the node. The easiest way to understand this formula, which is necessary in late times, is to remember, as I learned in the different lectures, that if you want to study physics of late times, behind horizon of the black hole, we can approximate the equations by considering the maximal extended Venn diagram from two sides of the black hole, where the mode that we are looking for now is the mode coming from the left side. And in this case, you can see that the algebras of the two sides are the same, but they're isomorphic. And that's why I say that the mode will produce effective theory at late times. We need to have the properties that the fields have an isomorphic algebra than the mode. But third, the fields as operators should compute the odds. Why is that? Well, these modes are coming from the left, these modes are coming from the right. In this approximation, these are state separated, so they should be independent. So at least at the level of effective theory, these two sets of operators should compute. As we see later, this may not be an exact statement, and particularly the way that we construct the fields, this equation, but this property is not inside. But at the level of effective theory, within the larger limit, these two operators will compute. These two sets of operators will compute. Finally, as we discussed many times, if you want to write this smooth, then the mode on the two sides of the horizon has to be entangled. So in this context, what it means is that these two operators have to be entangled by one, but by that I mean that they have to have the correct correlation functions. And to be precise, if you analyze the problem effective theory, you find that the property that this operator can satisfy is that this particular combination acting on the state side has to give you 0. This formula will stress the fact that these operators have to be correctly entangled. Now, we can summarize all these statements by saying that the correlation function that we calculate using the Boltzmann fields in R10 should be the same after one calculations as those that you would calculate in the two-sided geometry, where the fields are the operator on the left 15 and those on the operator on the right 15. And for those of you who are familiar with holographic interpretation of space-time, you know that this space-time corresponds to identical systems which are placed in a particular time state or the temporal state, where you somewhere both the identical states, both systems, and you have here the square root of 1 factor. So this is a particular time state which has the property that if you trace out one of the 15s, you recover an estimated estimates from the other side, and so the time correlators in geometry can be reproduced by seeing the correlators of the states. And what we say now is that the operator theta has a property that correlates between all n of thetas must be very close to correlators that we calculate on the state. And one more statement is that correlators of the state, two-sided correlators of the state can be related to analytic of the correlators of one side 60 against the several states. So if you're not familiar with the meaning of this state, you can ignore these last few comments, just to remember the properties that we demanded for the thetas, and let's go on. So the way we want to understand is whether the CFT contains these operators with the desired properties, and if we manage to find the operators, we'll argue that the CFT can actually describe the interior of the black hole, and that we have free and smooth space-time with the horizon and free input. So now the question is, how do we find the operators? The most nice thing you could try to do is to start with a collapsing black hole and take a point in that region and take one of these modes and try to trace it back using effective theory and see where it came from. So right after the collapse, you can actually do this calculation, right? So you can trace back these modes and you can see where they came from, and you will identify some operators in the conformity theory which can play the roles of delta theta for, let's say, a young black hole. However, as we try to ask the same question later and later, we have this property that Lars emphasized, which is that these modes, as we trace them back, get blue shifted. And very quickly, the energy at the center of mass of the collision becomes Transplanckian, and beyond that point, you can no longer trust effective theory. So it does not become a reliable computation to identify these modes by tracing them back and finding where they came from in the CFT. So there's one problem. There's one more problem, which is that, as we will discuss later, typical states in the CFT are not not those which are formed by gravitational collapse of the shell of matter. So if you look at the Bekenstein quantum entropy, you have a certain number of states which is predicted by the area of the horizon. So the number of states of a black hole is e to the s, where s is the Bekenstein quantum entropy. But then you can ask the question, is it possible to form all of those microstates by the gravitational collapse of a shell of matter? And the answer is no, because you can try to estimate what is the number of possible initial states of a shell of matter in ADS, for example, with given energy. And if you do that calculation, you can convince yourself that the number of states, the number of initial states of a shell of matter is parametrically smaller than the number of final states of a black hole. So by collapsing a shell of matter and waiting a little bit, you're not going to probe all possible microstates. You're going to probe only a very small subset. Said differently, we cannot produce a typical black hole microstate starting with the collapse of the shell. So even if we could follow this through and calculate where this O-tilde came from, those O-tildes we would not be able to apply them to a typical black hole microstate. So we're not going to follow this procedure. We're going to find a different way of constructing O-tildes. But already this is a bit discouraging, and now we present a few arguments which indicate that no matter how you try to find these O-tildes, you will not be able to succeed. So the first argument is a counting argument. So we start again with effect field theory, and we expand the field in modes beyond the tilde, and we calculate the algebra of these modes from the point of view of effect field theory in an approximation where those fields are free fields in the bar. So first of all, these guys will obey the standard algebra. These are creation and integration operators, and also they have certain particular commutation relations with the CFT Hamiltonian. So these are very standard. These commutations are telling us that if you act with bit dagger, so that bit dagger it should not have a subscript omega. So this bit dagger is an operator which creates a particle of frequency omega, and this equation is telling you that the CFT energy is increased by omega. So that's fine, that's normal. However, what is surprising is that if you look at the algebra of the bit tildes, the mode behind the horizon, you find that the commutation relation with the Hamiltonian has a negative sign relative to that one. So this means that if you add one particle behind the horizon by acting with a bit tilde dagger operator, you're actually lowering the energy of the CFT. And as you can imagine, this situation is not very good. It sounds like an unstable situation because you can keep producing particles without trains of particles without changing the energy, and you may expect that this type of computation relations will lead to some problem. And indeed, these authors, so Almeri, Marov, Polczewski, Stanford, and Stanley Stanford, show that this algebra is actually inconsistent with the spectrum of states of the conformal theory. So let's see how that works. It's a very simple argument. So from these computation relations, we can unambiguously identify that bit tilde dagger plays the role of a creation operator, right? So in particular, this equation predicts that bit tilde dagger should not annihilate typical states in the conformal theory. How do we see that? Well, I mean, it's very simple. You consider the state between the dagger acting on psi, and you try to compute the norm of the state. So you need to compute this object. And using that equation, you can rewrite it as psi plus psi b tilde dagger tilde psi. This is the positive operator, so the left-hand side has to be, this is 1. So the left-hand side cannot be 0. So this means that this bit tilde dagger cannot annihilate states in the CFT. It's not an annihilator. It does not annihilate any state. Now, on the other hand, we argue that this bit tilde dagger lowers the energy of the Hamiltonian of the CFT. Now, this means that if you look at the states of the conformal theory as a function of the energy, you have states of energy E. There are many states here, and then you have with this operator bit tilde dagger, and this subset of the Hilbert space is mapped to a subspace of energy E minus omega, where again you have many states. However, we know that in a CFT, in the reason of the CFTs, the entropy is monotonically increasing with the energy. So there are more states at energy E than at energy minus omega. So this Hilbert space is larger, it has a larger dimension than this Hilbert space. So this means that this linear operator maps a larger Hilbert space into a smaller Hilbert space. But that is impossible unless this operator has a non-trivial kernel on this space, right, the bigger Hilbert space. Which is in contradiction with the statement that this bit tilde dagger cannot annihilate any state, which follows from this equation. So this equation, together with that equation, is inconsistent on the algebraic level if we assume that the number of states on the boundary is a monotonically increasing function of energy. Now, you can also make this a little bit more precise as follows. Let us try to calculate the expectation value of the expectation value of the number operator for the mode behind the horizon. So we try to calculate this point. So, first of all, I will take this bit tilde dagger, and using this equation, I will try to commute it to the left of this factor. That you can do, right? And you get that when you using this equation, and when you commute bit tilde dagger through this exponential Hamiltonian, you get a factor of e to the beta omega, trace e to the minus, sorry, e tilde dagger, e to the minus beta 8 over z, tilde. Now we use the technique of the trace, so we write this as e to the beta omega, then trace of e to the minus beta 8 over z, bit tilde dagger. Then we use that equation, the fact that bit tilde dagger obey the standard computation relation of creation and relation operators, to rewrite this guy as bit tilde dagger bit tilde plus 1. So this becomes equal to e to the beta omega n, the thing we want to compute, plus 1. So we have this equation that n has to be equal to this. You can solve for n. Then you find that n, the expectation value for the occupation level of this mode behind the horizon, has to be equal to minus e to the beta omega divided by e to the beta omega minus 1. So this is a negative number, right? Which is clearly inconsistent for an operator which is not negative. So this operator, it's an operator times its dagger, so it's not negative. So no matter what this operator is, it cannot possibly have a negative expectation value. But that's what we found using this algebra. This equation together with that equation. So are there questions about this argument? So this shows that this argument shows that it is impossible to find an operator B tilde, and B tilde dagger is a performance field theory which obeys these two equations at the same time. So now you would ask, why was this problem not noticed many decades ago, right? I mean, this problem is basically, what we're doing now is effect field theory on this geometry, right? On the background of this geometry. So if in the real Davis, if they analyzed this problem of a black hole in ADS, they would have written down these equations, but why didn't anybody notice a paradox, many years before the final paradox? Why didn't anybody point out this paradox for this algebra? Well, the point is that the paradox arises when we demand that this algebra is realized on a very large number of states, to the point that we can approximate the results by this thermal trace. Because notice that in this argument, there was a step where we use the cyclicity of the trace, which we would not have been able to do if we had demanded that these equations are true only for one particular state. So if you demand that these equations are valid for just one state, you cannot run this argument through, and there's no contradiction. So if you do semi-classical gravity, if you do not have this very large number of states on the boundary, you just have one state, the semi-classical state of the quantum field, and there's no contradiction between that algebra and the state of the boundary. But if you demand that this algebra is realized for a very large number of states, and as a result you can approximate certain quantities by a trace, then you run into this paradox. Any questions? Okay, so this is a paradox that predicts that this operator between the dagger cannot possibly exist. There is a related argument which was formulated by Raphael and also Mark Polchinski, which is the following. So yesterday we wrote down the expansion of the Minkowski vacuum in as an entangled state between the two linear wedges, and we wrote the equation that if you look at one particular mode of frequency omega, the Minkowski vacuum has the expansion of e to the minus pi omega n times n left and right, and this particular expansion is precisely the combination that you need in order for this state to be annihilated by this operator, right? So the fact that the informing observer through the Riemann horizon does not see any particles relies on the fact that the Minkowski vacuum is annihilated by this combination, where for Riemann space beta will be equal to pi, and that's why we have this smooth horizon, because we have the correct entanglement. Now, if instead of the state we have considered the state where the left and the right modes have definite occupation levels, then of course on a state of this form there will not be the horizon will not be empty, there will be some particles, there will be some excitations. So if we want to have a state without an excitation of the horizon, we need to have the fact that it is a superposition of different occupation levels for the modes outside the horizon. Okay, so now let's see why this leads to a problem. This leads to a problem for the following reason. We can consider the operator corresponding to the occupation level of modes outside the horizon of the black hole. So let's consider the operator n, which is defined as the dagger t for some particular frequency. So this operator counts how many particles we have on the exterior of the black hole, and as we argued yesterday, this has a thermal expectation value, it's thermally populated. But this operator has the property, because this guy has frequency omega, and this guy has frequency minus, this is the dagger, so effectively it has frequency minus omega, this has frequency omega, so this operator has the frequency 0 in some sense, or in other words, this operator commutes Hamiltonian. This statement is not exactly true because it's true only in the larger limit, but for the purpose of this argument we can take a larger limit, and if you work a little more carefully you can convince yourself that the one-over-n corrections do not invalidate the argument that I'm going to present. So then what we're going to do is we will consider an operator which corresponds to what the informing observer measures. So that would be the number operator for particles in a particular mode of the field that the informing observer will detect. It will be a projector, which is 1 if the horizon is smooth, 0 otherwise. So it will be some observable for the informing observer. Let me call that observable A. So this is something that the informing observer will measure. And this observable will indicate whether the horizon is smooth or excited. Now, we will argue that there is a contradiction between the following statements. For typical states, which means for most black or microstates, A predicts a smooth interior. So let me make it a bit more precise. So let's say that we declare that if the expectation value of A is 0, then the horizon is smooth, or there are no particles in a specific mode. And if this one, then there's an excitation. So the first requirement is that for typical states we want the horizon to be smooth, which means that the expectation value of a typical state has to be equal to 0. On the other hand, we just argued before that for eigenstates of the number operator of the mode outside the horizon, the expectation value of A will have to be equal to, let's say, 1. Right? If you go back to the Minkowski vacuum, and if instead of this superposition you consider just one element where the number operator on the right is an eigenstate, that's an excited state. There are particles across the horizon. So if you fall into an eigenstate of this mode n, the informing observer will detect some particles. Right? So we have these two conditions which seem to follow from effective theory and from our desire to demand that the horizon is smooth for typical states. And these two are in contradiction for the following reason. If this equation is true for typical states, then it means that if you also compute a trace of this operator A, over the ensemble of states of given energy. So let's introduce the microcanonical density matrix here for states of energy between E naught minus delta and E naught plus delta. We consider all possible microstates in that energy domain, and we compute this expectation value. According to the first equation, this would be equal to 0, or at least approximately equal to 0. However, because the Hamiltonian commutes with the number of operations of the exterior, these two operators commute, this means that you can find simultaneous eigenvectors of the two operators. You can diagonalize them simultaneously. In other words, if you look at the subspace of states within that energy range, you can select a basis in that subspace where the basis elements are eigenstates of the operator n.